So regularization is a word that is super important and super central to all of machine learning, and not just neural networks. Um, and here's the context. Neural networks, especially deep neural networks, have lots and lots of parameters, like namely weights and biases is what we mean by parameters here. So because they have a lot of these little knobs that you can tune to fit a complicated function, or basically fit a very complicated data set, they have the potential to overfit even very large data sets. So if you increase the number of layers, and if you increase the number width of the layers, you have lots of parameters to tune, which allows you to tune them in a manner that you fit incredibly large data sets. And if you exactly pass, in some sense, the neural network through all the data points, then you have the potential, let's say, to overfit the data, right? Just like we had the potential using to overfit data using polynomial functions, we can do that with neural networks as well. The same issues and the same dangers are here as well. Um, and in fact, in modern deep learning sort of neural networks, the number of unknowns, namely weights and biases, may actually far exceed the number of data points, which is surprising. But that happens. In fact, happens often. So how do you ensure that you do not overfit? And how you ensure that you do not overfit is basically at least one way of not overfitting is called regularization. Okay, and regularization is not necessarily one single thing. It's lots of different things which have the same flavor. Um, Let me discuss briefly a couple of examples. Um, they are basically L1 regularization and L2 regularization. These are just a couple of examples. Um, what do these words mean? So in machine learning, let's say you're doing classification. What you're doing is usually minimizing the loss function, right? So things like least square error, mean square error, or logistic loss, or constant entropy loss function. Um, Instead of just doing that, so if you did that, then of course the optimization will try to find um, the parameter values so that you uh, perhaps drive the mean square error to zero, or um, cross entropy loss to zero as well. Okay. Um, Now, instead of doing that, and that uh, exposes the possibility of overfitting, just having or just minimizing the loss function. So instead of just minimizing the loss function, what we do is we add another term to the objective function, um, so that you minimize not just the loss function, but loss function plus actually square sum of all the parameters of all the weights and biases. If you add the squared sum, or sum squares of all the parameters, that's actually called L2 regularization, because this is related to what's called the L2 norm. If you take the square root, this is the L2 norm. And similarly, you can add to the objective function, in other words, in addition to the loss function, another function that you minimize. In other words, you minimize the sum of these two things. If the other function is sum over all parameters of the absolute value of the parameters, that's called L1 regularization, because this is the L1 norm of all the parameters. Okay. So just to take it as a precise example, instead of minimizing the MSE or cross entropy, we can minimize MSE plus lambda times epsilon, sum over parameter I square, or lambda times sum over absolute value of parameter I. Okay. If you minimize this, let's say where you're trying to fit some function, that's called ridge regression. And if you minimize this, it's actually called lasso regression. Um, you can look those names up if you want to learn more about why they are called that. But in any case, Conceptually, relatively simple. You just add these additional terms, okay? And then you add it, you just don't add exactly that function, but you weight it so that you can sort of change how much mean square error is important versus how much this is important, okay? Um, so let's talk about this lambda. If lambda is equal to 0, then of course you're just minimizing the mean square error, right? If lambda is larger, then what happens? Imagine lambda is super large so that this term totally dominates the objective function. In that limit, where the mean square error doesn't matter at all, where you're just minimizing this, then the solution to that optimization problem is all the parameters are equal to 0, right? Because if you set all the parameters to 0, then this term is as small as possible, and this term is as small as possible, right? So what happens is when lambda is equal to 0, you just minimize the mean square error. And when lambda becomes larger and larger, the values of the parameters become smaller and smaller, closer and closer to 0, okay? Um, so that's the basic mechanism, very simple. Okay. What is the effect of having the parameters, namely the weights and biases, close to 0? Um, the effect is basically that you're sort of constraining, in some sense, um, the weights and biases to be in a narrow region of possibilities, namely relatively close to 0, which means that the function approximator, namely the neural network, um, cannot be arbitrarily complicated, right? If the weights and biases could be whatever they want it to be, you could potentially approximate really complex functions, and by containing the weights and biases to a small region, or basically making sure that they're relatively small, you may not be able to produce really complicated wiggles with your neural network functions. Okay, so that's the main mechanism, and by reducing the complexity of the functions, uh, well, you are essentially preventing it from overfitting, right? So because overfitting is about having the flexibility to go through every data point, but if you do not have the flexibility to go through every data point, you might make the overall function sort of more smoothly changing, as well as maybe you won't exactly pass through the data point. Maybe you will only approximately pass through the data point so that you reject, for instance, noise in the data set. Okay. Um, okay, so that's basic principle of this kind of regularization. Um, this kind of regularization can be applied to neural networks, or they can be applied to any kind of function approximation, really. They can be applied to polynomials, for instance, like we discussed earlier in the course. We could use that, like we were trying to figure out what the optimal order of the polynomial should be. Instead, we could add a regularization term to keep the polynomials from wiggling too much. Okay, um, and then you get into the question of how do you fix this lambda value, which we will talk about in a minute. So that's note number one. You can apply to neural networks, but you can also apply it to quadratic, cubic, polynomial regression, or anything else in between. Okay. The second note I wanted to make was that L1 regularization. So both of these have the effect of reducing the parameters. L1 regularization has sort of an interesting and useful property. It actually makes a solution sparse. What does that word sparse mean? Sparse means that if you have a sparse matrix, for instance, is something that mostly has zeros and has a few non-zeros. And when we say the solution is sparse, this we are referring to the solution for these weights and biases. Um, when you say the solution is sparse, what we mean is many of the weights and biases become equal to 0 when you optimize this function, and some of them are non-zero. Okay. The effect of setting a whole bunch of weights to 0 means that what you're doing is when you have a fully connected neural network, for instance, um, you are removing some of the links between neurons. You're sort of simplifying the neural network a little bit. So L1 regularization has that interesting property. Okay. Okay. So that's all I wanted to say about regularization, at least of this kind of regularization for now. Uh, okay. So I just said, how do we pick this lambda? If lambda is 0, you just care about the last function. If lambda is large, you just care about reducing the parameter size. But you want some optimal sort of lambda level so that you do reduce the mean square error a lot, or whatever the last function may be, but you don't let the parameters go too high or make the function overfit the data. Okay. How do you pick the optimal lambda? Or more generally, how do you pick the optimal learning rate, the optimal momentum value if you're using stochastic gradient descent with momentum? How do you pick this regularization penalty, lambda? More generally, if you have a neural network and the learning algorithm for that, we might also want to pick the learning rate decay. We were talking about learning rate scheduling, where you change the learning rate once in a few epochs. So how do you pick how many epochs and how much you change it by? Um, Even more sort of crucially, how do you pick how many layers your neural network should have and how wide your neural network should be? In other words, how many neurons in each layer? Okay, so these are all questions. Um, these are all parameters, um, which are actually called hyperparameters for some reason in machine learning. An example of a hyperparameter is actually the degree of the polynomial in our old polynomial regression work. But here it's got to do with all these things that um, talk about the um, architecture of the neural network, or here the architecture of the optimization algorithm itself. Okay. So how do you pick these hyperparameters? They're called hyperparameters because they're sort of, in some sense, sitting on top of parameters. They have a higher status than the regular parameters, which are the biases and weights, okay, of your neural network. Um, so we can pick most of these things if you have experience handling a particular kind of data set or using a particular kind of algorithm. You can use experience. If you're using a similar kind of data and some parameter values work for some data set and you're using another data set that is similar to the old data set, maybe you can use the same values. You can do trial and error where you just try out a few different things and see what works best. Formally, picking good values for these parameters is sometimes called hyperparameter tuning. And we could do this the same way that we pick the optimal value for the polynomial degree, right? In your old first few lectures, we picked the polynomial degree of the polynomial via a process called cross-validation. Essentially, or at least one version of the cross-validation technique is you have a training set and a test or a validation set, and then you fix all these parameters, um, and then minimize the training error or whatever you want to minimize, and then uh, test it, test the results on the test or the validation set, and then redo that process with different values of these parameters, these hyperparameters, in a manner that you have the best possible accuracy on the test or the validation set. Okay, so you train on the training set, and then you evaluate the goodness of your hyperparameters based on your accuracy on the test set. Okay, and this will make sure that, or at least help not overfit the data. Um, of course, this is some kind of an optimization problem. There's an inner optimization problem where you fix all these parameters and then tune all the weights and biases to fit some function. And then there's an outer loop optimization where you're changing these parameters, hyperparameters, in a manner that your optimization algorithm itself proceeds much better, okay? Or your results are as good as possible in terms of the training test accuracy. To solve this optimization problem, of course, you can use trial and error. But people these days use various techniques. I will just mention it. We're not going to necessarily explore any of these in detail here. We could use gradient descent. There's an algorithm called Bayes optimization or Bayesian optimization, which we might spend a lecture on if we have time. Or you can just test at random points and pick whatever is best. Or you can use a grid of these hyperparameter values and systematically do an optimization for each of them and see which works best. So you can do all these things, okay, to pick the best values of these parameters, and that's called hyperparameter tuning. Ideally, when we do these neural network optimizations or training, we want the training error to be as close to the testing or the validation error as possible. If they are too far apart, in other words, if you have good training accuracy but really bad testing accuracy, then it sort of means that overfitting is happening, and we may need some regularization to bring those two in line with each other. Now, of course, if you regularize too much, in other words, you pick too large a lambda, you'll get bad training error as well. So there's a balance there.